Here are a few examples from section 16.1 to 16.3. In these two problems from 16.1, we're asked to find the gradient vector field, and in 26, we're also going to graph the gradient. So when we're constructing a gradient from a 2 or 3 variable function, what we're doing is we're creating a vector field whose component functions are the partial derivatives of that multivariate function. So in the first case, my gradient is partial with respect to x. Partial with respect to y will require the product rule. And partial with respect to z. So that was chain rule on that last one. So there's your gradient vector field, and I don't really want to graph that at all. Thankfully, they didn't ask me to. In 26, it's a little bit easier, so let's crank out that gradient and graph it. So to graph a vector field, I think plotting points, or like plotting vectors, I guess, is the best thing to do. So I'm going to pick some easy values for x and y and compute what the gradient vector is at that pair xy, and then graph off to the side. Okay, so here are the ones that I chose. Okay, and then when we're graphing the vector field, what we're doing is we're locating the point xy, in this case 0, 0, let's say, and then we're drawing the vector that's associated with that point. So in this case, it would be the 0, 0 vector. Drawing a dot is sufficient for that. Next, so I go over to the point 0, 1, which is here, and I draw attached to that a vector 0, negative 1, so that this vector has x component 0 and y component negative 1. So that would look like this. That is the vector 0, negative 1. Okay, so I'm just going to continue doing that until a picture emerges. Okay, so after graphing, I think I got all these vectors. Yep. So after graphing these 9 vectors, I get a sense for how the vector field is behaving. You see that there's sort of like in the upper half plane like a downward flow, and it's sort of going outwards at either end of the x-axis. And then in the lower half plane, I see an upward flow towards the x-axis, going outwards at either end of the x-axis. Okay, so this is just sort of like practice taking partial derivatives and plotting a vector field. Okay, in 16.2, we're computing line integrals. So I want to practice with this one here. They have parameterized a curve for me, but like in general, they may describe a curve, and you have to parameterize it. Remember how to parameterize like semicircles, circles, line segments, and so on. You may have to do that to set up the line integral. But they've given us a parameterization. You may recognize this curve as a helix, a part of a helix, and we're going to compute this line integral along it. Okay, so remember that the ds unit is the sort of differential of arc length. So I take the derivative of the vector function that describes the curve and square the components of that derivative. So let me write this out explicitly. If r of t is this, then I'm taking r prime of t in magnitude is what the ds is. Okay, so 1 plus 4 sine squared 2t plus 4 cosine squared 2t. And this reduces, since I've got a sine squared plus cosine squared, I just get 4, and then plus 1 is 5. Okay, now I can set up my integral. X squared is t squared, y squared, and z squared. I have another cosine squared plus sine squared. Okay, and there you go. Let's compute another line integral. This line integral is going to be the work done by this vector field in moving a particle along a line segment. So the work done is the line integral of the vector field along the curve. This is the notation for that. In order to compute this, I'd like to parameterize the curve and compute out the integral. I can avoid doing this if the vector field happens to be conservative. We'll see that in the examples that I chose from the next section. That is a shortcut for getting it computed. But this vector field, unfortunately, isn't conservative. Okay, so C is a line segment. Here's the trick for parameterizing a line segment. What I do is I put 1 minus t next to the initial point, which is 0, 0, 1 here. 0, 0, 1 plus t times the terminal point, 2, 1, 0. And this trick will get the line segment parameterized in 1 second. So the x component here is 2t, y component t, and z component 1 minus t. So here's your parameterization of that line segment connecting 0, 0, 1 to 2, 1, 0. Okay, we're also going to need then the derivative of this vector curve, and then we fill out the line integral. So integral from 0 to 1, we're going to plug the parameterization into the vector field, and then dot that with the r prime. Okay, so I need to plug these into the vector field. Okay, so there you go. That is the work done, 7/3, whatever, Newton meters or whatever the units are. Okay, let's move on now to section 16.3, which is about using the fundamental theorem of line integrals. Okay, so they ask us to use the fact that this is a conservative vector field to compute the line integral of the vector field along the curve. So step number 1, or step A, I guess, is to find a multivariate function so that the vector field is the gradient of that function. And in that case, the fundamental theorem of line integral says that I can compute this in sort of a fundamental theorem of calculus way. I just take that antiderivative, little f, and plug in the starting and ending points of the curve. So, okay, part A is find a function whose gradient is equal to f. So if I'm trying to find a function, a multivariate function, whose gradient is this vector field, then the partial derivative of that function with respect to x must be this expression here. So that gives me one view of what the function f is. If I anti-differentiate this expression with respect to x, then that will recover some of the terms of this function f. So that's what I'm going to do right now. I'm going to take the antiderivative of this expression with respect to x. So that'll look like this. And of course, the issue is antiderivatives are not unique, right? And when I take an antiderivative with respect to x, there's a constant term, but constant means it may depend on y and z, because if x is the variable, y and z are constants. So to account for that, I just put a placeholder for a term that may depend both on y and z that I wouldn't have discovered just by anti-differentiating with respect to x. So and then I'm going to move through the other variables, and all the terms of f will eventually be revealed. So in this case, I'm going to get another sort of estimation of what the f function is by knowing that the derivative of f with respect to y is this expression here. So I'm going to anti-differentiate this with respect to y, and that gives me this. And I understand that with respect to y, there could be x and z terms that were not detected by this antiderivative. In fact, like if I just glance up to my previous estimation for f, I see that this antiderivative didn't detect the x squared z squared term, Okay, and then lastly, I get the third view of what f is from the antiderivative of this expression with respect to z. So antiderivative of this plus antiderivative of the second term with respect to z. And again, I don't know if there are x and y terms that were undetectable by this antiderivative. And so once you line these three things up, you can deduce fully what f looks like. Every single one of the antiderivatives picked up this term, right? Because it has x's and y's and z's. In my first and last computation, I was able to detect this term, but the antiderivative with respect to y didn't pick that up, but I know that there's an x squared z term from the first line and the bottom line. And there apparently is no term that solely depends on y and z or x and y, because that was not picked up in any three of the antiderivatives. So I know when all is said and done, putting these all together, that the function must look like this. xy squared z plus x squared z squared. And you can always check to see if you get the right antiderivative. Just take your gradient here and see if it's what you started with. There's a common mistake to want to like add these functions together, but you're not adding these terms together at all. These are just different views of the exact same function. So we don't want three of these terms or something. It's just this term is getting picked up by each of the three perspectives. So like if you do something wrong in that step, you'll see it when you try and take a gradient here, and it won't look like what you started with. Okay, so now we can very easily compute the line integral of this vector field knowing its potential function. So the line integral of f dr is simply the potential function evaluated at the ending point of the curve minus the potential function evaluated at the starting point of the curve. So let's come back here to the curve. It's parameterized for us from time equals 0 to time equals 1. The ending point is this parameterization evaluated at time equals 1. So that's 1, 2, 1. And then the a is the beginning point. That is 0, 1, 0. So to compute this line integral, I plug in 1, 2, 1 to the potential function, then 0, 1, 0. And I get here's the function here. I get 4 plus 1 minus 0. So it's 5. And you can see that this is much quicker than computing this line integral from scratch as we did in the previous section, because that would require plugging the parameterization into the vector field, look at all these terms and squares and everything like that, and then dotting with the derivative of this vector function, right, which would have some awkward terms involving t, and it would just involve a longer computation. So this is the time savings of the fundamental theorem of line integrals. Okay, so let's go ahead and use the fundamental theorem again to compute the work. This question is asking you to find the work done by this vector field in moving a point from here to there. If they haven't specified a path from here to there and they're telling me to use the fundamental theorem, then I understand that this is a conservative vector field and hence it's path independent. So let me go ahead and try and find my my potential for this vector field. I think I can just eyeball this one. Like, in order for this to be the partial of f with respect to x, I definitely have to have this right here. And I can just check really quickly that the partial of this with respect to y is already x. So I found my potential quite easily. So the work done is the line integral of this vector field across basically any curve from here to there. And now that I have my potential, I can just plug in the ending point minus the initial point, and there you go.